By the end of this video, you will be able to ship your code across systems like a submarine in the ocean. This is you, a skilled data ninja, have developed a smart machine learning script using Python 3.10 on your Windows machine. However, and here's the catch, your boss, an Apple user, is running Python 3.7. The challenge? Your boss needs to execute and use your script. Here where Docker shines, the ultimate solution for seamlessly shipping code across diverse systems. Just like a submarine stocked with oxygen, food, and all essentials for human survival underwater, Docker encapsulates your code and its dependencies into an isolated container and make it ready for any environment. To comprehend how Docker operates, there are four crucial concepts to grasp. We will get into each one shortly, but here's a brief analogy. A Docker file serves as a manual or a set of instructions for constructing the submarine where your code will reside, detailing the materials, oxygen level, pressure, and other vital specifications. Secondly, an image. Just imagine we want to sell this submarine on Amazon. You would need an image for the final product to show it for other people to buy. It provides a comprehensive description of the submarine container in which your application will reside. It's important to understand that an image is not the physical submarine itself, it's just an image of it. And this brings us to the third concept, the container. This is the physical submarine of your application. This is where your application finds all necessary dependencies encapsulated. The fourth concept is Docker Compose, which serves as your automated system, takes care of container management and making the process significantly easier. Let's dissect each one of these concepts. Dockerfile. A Dockerfile, typically named Dockerfile with capital D, acts as a recipe for building your code submarine. This file resides on your PC, for example, on your Windows system, within your app folder. And let's break down its components. The first line of the Dockerfile typically employs the from keyword, defining what known as a base image. It's akin to selecting the material of your submarine. This step contains the essential operating system and other dependencies required for your application to run. For instance, if you're developing a Python application, your code might start with from Python 3.10. Here, the Python 3.10 represent that inside your submarine, we set up a Linux operating system and installed Python 3.10. So no matter what operating system your boss is using, your code will run on Linux and Python 3.10 as it's encapsulated inside the submarine. The second line sets the working directory for any subsequent command using work_dir or like working directory instruction. It's like creating a folder named my app and cd into that folder. The third line, utilizing the copy instruction, copies file from the host file system, in this case my Windows machine, into a Docker image at a specified destination. The signature of this command is the keyword copy. Then you specify the relative path of directory you want to copy from your PC, and then the relative path of the destination you want the folder to be copied to. In this case, the dot indicates that Docker should copy all files and directories from the current directory on the hosting machine, where the Docker file is located, into my app directory within the Docker container. Remember, we cd into that folder, hence the dot. Notice that the data folder here is not copied across, which is a best practice to keep the data private and keep the image size small. However, we have an empty folder here, a placeholder folder called app data. We will discuss more about it later. I promise it will pay off at the end. The fourth line, employing the run instruction, executes commands in Docker containers shell during the build time, akin to opening the terminal in your container and type pip install command to install the Python dependencies specified in the requirements lab.txt file, ensuring that the required Python packages are installed and available for the application to run successfully. The expose instruction informs Docker that the container listens to the specified network port at runtime, same as you open your browser and type localhost 8888 to access Jupyter Notebook or Jupyter Lab servers. Lastly, the cmd instruction specifies the default command to be executed when the Docker container starts, launching Jupyter Lab within the container, configuring it to listen to all available network interfaces and disabling automatic browser opening and allowing the root access. All of these are seen to be best practices when using Jupyter Lab. So in summary, Dockerfile defines a series of instructions to build the Docker image for a Python-based application. Now that we understand the content of the Dockerfile, let's explore how we can use it to create the image. Firstly, you need to install Docker on your system. The link for installation can be found in the video description below. Then, ensure that you are in the same directory where your Docker file resides. Navigate to that folder and run the docker build command, specifying the name of the created image using the T flag. I'll name this image as my first image. Notice the dot at the end. Think of this dot as a pointer indicating where Docker should look for the files needed to build the Docker image. Docker images are read-only, meaning you can't edit them or make changes to them. However, you can overwrite them. And I'll delve into this later. The created image will be stored in your system. Know that from this image, you can create your submarine, the container. In fact, you can create as many containers as you wish. Let's now proceed to creating our first container using the following command. Now, this command might look a little bulky, but I promise that I will show you a trick that make it a piece of cake. The docker run command instructs Docker to run a container based on a specified image. The name flag allows you to assign a name to the container. In this case, I'll choose container 1. The IT flag ensures that you can interact with the container's terminal in an interactive session. Think of it as if your app spits logs, you will be able to see them in your terminal. Remember when I mentioned that the data folder wasn't copied to keep the image size small? It's time to address that. How do we access the data? We have our data folder residing on my PC, and I want to connect it to the app data folder without copying the data. This way, we can keep the data separate from the container. Just in case the container is deleted, we don't want to lose any data. To link these folders, we use volumes in Docker. In the terminal, we add the v flag and specify the absolute path of the data on my PC and its destination in the container as follows. Similarly, we want the changes in the code to be saved outside the container. This is particularly useful for development, not deployment, as you often need to modify the code and see the changes without rebuilding the image. So we apply the same volume concept between these two folders. We add the v flag and specify the absolute path of the code folder on my PC and its destination in the container. Finally, I know that the Jupyter Lab will be exposed using port 8888 as is specified in the Dockerfile, but it's within the container. I want to access it from my machine. This is where port mapping comes in. Using the P flag, we map the port used in my PC browser to the port in the Docker container 8888. So when I type localhost 8888 in my PC, it will be mapped to port 8888 in the container. That lengthy command will build and run the Docker container. Docker generated a localhost link to us with port 8888. Clicking on that link, Jupyter Lab will pop up. We can check app data folder in our Jupyter notebook, and we will see that it reads data straight from our data folder in our PC, and running that notebook will produce a new CSV file which will also be stored in our system straight away. Similarly, if we change the code, it will also be reflected in our container. And notice how the highlighted comment will change when I save the Jupyter notebook. Let me put them side to side. I'll save that, and here the word another is added. If you think that it's a very long command, you are right. And this is why it's time to introduce Docker Compose, where we can automate this entire process. Docker Compose is a tool used to define and run multi-container Docker applications. It allows you to define services, networks, and volumes needed for your application in a YAML file called Docker Compose. Let's break down each part of that file. The version specifies the version of the Docker Compose file syntax being used. Here I'm using 3.8. Services defines the different services that make up your application. In our application, there is only one service, but if you have more complicated application with backend and front end, each one of them is considered a service. In our application, there is one service, my app, the name of the service. And then image name, I'll choose my second image, specifies the Docker image to use for my app service. And then the container name, I'll go with container 2. Then we have the build that indicates the Docker Compose should build the image using the specified Dockerfile, and the context is the dot, as we explained earlier. That means the current directory where the Docker Compose.yaml file is located. Then Dockerfile specifies the name of the Dockerfile to be used for building the image, and then we specify the ports and the volumes, same as we did before. And then these two lines just to ensure the interactivity, same as the IT flag we talked about earlier. So as you can see, we have in Docker Compose all information we initially use in our lengthy command. So to start, create, and run the container, we simply run Docker Compose up. Or if you want to rebuild the Docker image, you can use Docker Compose up --. And same as before, a new image will be generated. And as you can see here, I have my first image and my second image, as well as the second container that I created. And we will have the same behavior as before by linking the code and the data folder into our system. So for example, if I run the Jupyter Note by changing the name of the output CSV file, I'll find that CSV file straight away in my data folder. And let me change that comment. It will be reflected as well. If you learned something new, please hit like, share, and subscribe. See you in a week's time.